We've talked before about high-pass and low-pass filters, passive ones where there's just resistors and capacitors and perhaps inductors. And we've had examples with op-amps as well, but I want to talk now about making active filters in general. An active filter is one in which there is an op-amp. And with that, we can have a filter whose gain is greater than unity, but still has a high pass or low pass characteristic. So first consider our negative op-amp amplifier with general impedances. And in particular, I want to consider impedances here that are made out of resistors and capacitors. And we can put those resistors and capacitors either in parallel or in series. So let's just quickly go through what those look like. If you have a resistor and capacitor in parallel, then you just combine their impedances like this. Sum of impedances on the bottom, product on top. That's the way we combine impedances in parallel. And when you multiply this out and simplify, you get this nice form, R over 1 plus RC times S. And so this function has one pole in it at S equals minus 1 over RC. Now if you put the resistor and capacitor in series, you just add the two, and when you combine them in the way we've been doing, then you get 1 plus RCS on the top, and that's divided by CS, and that has a root and a pole. The pole in this case is at 0. Then now if we combine those in the negative op-amp amplifier, we're going to divide by Z1, and this should be Z1 here. Any roots in the Z1 will become poles in Z2. So specifically, let's think about the case where the series are in front and the parallel are the second term. So plugging into what we had before, I just put R1 and C1 in for Z1 and R2 and C2 in for Z2. And then the gain, we already know, is minus Z2 over Z1. So I've written that here. I've already flipped over Z1 here that we divide by, so I just flip it over. And so we quickly notice that we just multiply it out. This is the same as that. I've just replaced R2C2 by 1 over nu2. In other words, there's a frequency that goes with 1 over RC. And I've plugged that in, but I've kept out the R2 and the C1 that appear in the numerator. So we have a function that has two roots, two poles, and one root. The shape doesn't really depend on whether omega 1 or omega 2. Sorry, I switched from the last one, from nu to omega. It's still 1 over RC. Doesn't matter which of those is greater, which of the frequency associated with this or the frequency associated with that, which is bigger. But it determines what the actual gain is at the top. So if R1C1 is bigger than R2C2, in other words, 1 over R1C1 is less, so it comes first. Then when you work all this out, the gain at the flat top of this thing is just going to be R2 over R1 as you expect. It's a minus, but that'll become in the phase. If you switch the order, then it turns out that the gain at the top is C1 over C2. It's flipped over because of the 1 over C nature of the impedance for a capacitor. And so when we look at this, then we can plot it using our Bode plot methods, and we notice there's a root at 0, so we expect this rising line. And then we have two downward shifts at omega 1 and omega 2, and here I've put them at 100 and 10,000. This is the log of the angular frequency plotted here. And the gain in decibels here. So we go up, we turn, we go flat, we turn, we go down. 20 decibels per decade going up, 20 decibels per decade going down. We have a flat top. If you actually plot this to take the magnitude of this as a function of omega, where s equals j omega, and calculate it, then you get the red line here. And you can see how well that compares to the Bode plot. Notice at the frequency values here and here, we're down by 6 decibels from the corner of the simple Bode plot. Can plot the frequency as well. We have a minus sign there and a j from the s, so we start at a frequency, at a phase of minus pi over 2. Omega 1 in this case is 100, so we go from, and it's a pole that we're doing, so it makes us go down by pi over 2 from that pi over 2. So we go down over those 2 orders of magnitude. And then we're going to go down further, but that flips us over to the positive side of pi. And we go down further for the second one, which is centered here. Again, we go from minus pi, which we flipped over to pi, and we go down further, we subtract another pi over 2, we end up at pi over 2. And the black lines are the Bode plot as we've learned to draw them. The red lines are the actual phase of this function. Okay, so now let's move on to an active amplifier which has multiple feedback loops. And in this case, we can get more interesting behavior. One that'll have a resonance characteristic. So you can imagine, so here I've just drawn a sort of a general way to have 2 feedback loops. We can come this way, we can come back that way, and we can analyze this circuit just using the node method. I'm doing that kind of implicitly here, but we can go through. So first of all, the voltage drops from here to here by I1 Z1, so that's the first equation. Or in other words, to get from the voltage here back to Vs, I have to add up Z1. Notice I've put Vs here as a source term and the unknowns Vb and I1 on the right. That'll make it easier to do my linear algebra calculation at the end. Okay, so I just go through I3 Z5. Well, this is 0. I'm coming down from V0. So that gives me this equation. That same I3 goes through Z3 to get to VB from 0. So that gives me this equation. I go from V0 through ZA to VB. That gives me this equation with I2. And finally, I2, I1, I3 all combine to go through Z2 down from VB to ground. So that gives me 5 equations in 5 unknowns. V0 is one unknown, the voltage here is the unknown, and the 3 currents. So if I arrange those as a matrix, and then I can get this series of equations by this matrix. So I've arranged the columns of this in this kind of funny order that puts columns with lots of entries to the left. That's the only reason I picked this order. And then, so now I really don't care what the currents are. All I really care about is what V out is. And so I can use Cramer's rule to solve for V out. Cramer's rule says that the value for any of these variables is the determinant of the array when I replace the column for that variable with the source term. So in this case I want V out, so I replace the last column with V sub s down to 0. You see there's my matrix, and I take the determinant of that, and then I divide by just the regular determinant when I don't change anything. When I do that, I get this formula, which is not so bad, for the gain. You can work that out yourself. I'm not going to take the time here to do it. Hopefully I did it correctly. Now, it only becomes interesting when we actually put in resistors and capacitors for these undefined z's. So let's take the case where 1, 3, and 4, 1, 3, and 4 are resistors, and 2 and 5 are capacitors. In that case, we get a low-pass filter. So I take my equation from the last page, I plug in the impedances as appropriate for each one of those. So Z4 is a resistor, so I just plug in R4. Z2 is a capacitor, so it's 1 over C2S. And so I get this general equation, which I can recombine into this form. Notice that I've done what I usually do. I have no s's on top, and I have a polynomial in S on the bottom. I've also made it so that the highest part of the polynomial in the bottom, the S squared, has no cofactor. So when I have it in this form, I can then rewrite it in a sort of a standard form where I have S squared plus S, but here I take alpha omega naught times that, and then I take my constant term and call it omega naught, and then what I have left up on top is another constant times omega naught squared. In this case, H naught will be R4 over R1. Omega naught will be square root of 2 RC squareds, so but 2 R's, R3 and R4, and 2 C's, 2 and 5. And finally, when you work all that out, alpha is this kind of messy combination of resistors and capacitors. What you get, this form here, is the standard form for a low-pass transfer function where you have a complex conjugate pole pair. In other words, you have two poles in the bottom there because it's a second-degree polynomial, and it turns out that they are a complex conjugate pair. In other words, the real part is the same and they have opposite imaginary parts. Now it turns out that if you can change alpha here by changing the resistor values, you can get interesting behavior. If alpha equals 2, then we basically have a quadratic that we can solve. It actually has 2 real roots. But if alpha is less than 2, we can only get pole pairs. So the alpha equals 2 case is this purple line. But if we make alpha 1, for instance, we get this blue line, which notice right at the characteristic frequency, omega naught, when omega equals omega naught, we get a gain of exactly, 1 over of H naught, which I've divided out here in this plot. So as we make alpha much smaller, we go up and get this peak structure. So in general, the way to draw a Bode plot of these kind of things is to figure out what alpha is, and then you draw in the straight line to the characteristic frequency. You go down at the straight line, but now not at 20 decibels per decade, but at 40 decibels per decade. And then finally, you draw a line going up, which will be the log of 1 over alpha. So if alpha is 0.1, then we have a gain of 10 there, basically. And that's, in fact, this case. And then we take the log 10 of that, multiply by 20 to get 20 decibels there. So that's how you make a Bode plot of this, and then you estimate this gain. If we replace all the capacitors and resistors with the other kind, we get a high-pass filter, which has this standard form where you have these values. Notice that the omega naught squared I had before has been replaced with an omega squared. That's indicative of the high-pass nature of it. And so this is the standard form complex conjugate pole pair for a high-pass transfer function. Rather than remake the figure, I just flipped it over. This is the same figure I had on the last page. I've just reversed the direction of it. So it still goes from -1 to 1. It's just that it's a high pass, so it has to be 1 here and going up there. You're going to need to use this in the lab, in one of the labs. So how do you go about designing what the filter parameters should be? Well, there's really only 3 parameters, H naught, omega naught, and alpha, but we have 5 components, so we have some choice. And in fact, we're going to restrict that further and make the gain in the pass band equal to 1. So to do that, we're just going to pick all the resistors to be the same, leaving us with only capacitors to pick. In that case, when we work everything out, H naught is 1. Remember, it was the ratio of resistors. Omega naught is 1 over RC, where we have the R for the 3 resistors, and we take the geometric mean of the 2 capacitor values. And alpha is 3 times the square root of the C5 over C2. So if you want a given gain here, you set alpha and the ratio of the two component capacitors here, and then you set the size of them to give you the frequency you want. Okay, the final topic for today is how you make an oscillator. And an oscillator comes from having a filter that has a pole in it when we write down the transfer function. It has a pole that has a non-negative real part. Now, a non-negative real part means that it's a growing exponential, and if it's only slightly greater than 0 and can be pulled back to 0, that means you basically have a sine wave at all time, and you can then, it's your active filter, quote, filter, that's producing the energy to make this sine. To understand this, I need to introduce just a little bit of signal and feedback theory. In signal theory, we have a bunch of very abstract components. You put a signal in and you do something to it. A triangle scales it. It looks like an amplifier, and it is an amplifier. It just multiplies by a certain amount. You can combine signals like this. You just add them together in this case. That's what the sigma means, sum. And you can modify it with some function. Here I've put s in to indicate differentiation in the Laplace transform sense. But we're not actually going to use this very much. Now you can imagine what feedback looks like in this system. You can take some general signal, do something to it, and take part of it, do something to the product of that, and come back and bring it in. And as it's indicated here, this is actually positive feedback, unless there's some negative sign there. And we're most interested in the case where we just have simple feedback. We take the signal, we multiply it, and we take some part of it and feed it back. So we're multiplying the output by some factor. So in this case, it's easy to calculate what the output is. So the output is A times what comes out of here. So here's my A, and A is V in plus beta times V out. That's what I have there. Now when I solve for V out, I bring it over here. I have a 1 minus BA. And so the gain of this simple feedback system, the output over the input, is A over 1 minus BA. Now, we often will have A very large, in which case the gain is minus 1 over beta. But if A is not large, I can get an infinite gain if beta A equals 1. And what that really means, an infinite gain means even with 0 input, I can get an output. And that's what I want to create an oscillator, which is, after all, putting out a given frequency with it, even though we don't have any input. Okay, so now consider, to make this, we're not going to worry about going to the frequency domain plane or anything. We're just going to analyze this situation. Imagine that I have an amplifier that's not an infinite gain, but it has some finite gain A, and I have a voltage divider chain with impedances, and it's positive feedback. Now, I have a V out, and I'm comparing V out to some voltage here, and so I know what V out is. It has to be some fraction. So V out comes from A times this, and the voltage here is just Z1 over Z1 plus Z2 times V out. So I have V out equals that, A times the voltage divider times V out. Now for that to work, I can cancel the V outs, and I must have A Z1 over Z1 plus Z2 equal to 1 for this thing to be in any way stable. And so this is called a Wien bridge oscillator. And the way I get these things to be 1 is that I have it, for some particular frequency, work out to be that way. So in this case, I'm going to take, again, resistor and capacitor in parallel and in series, and in particular, I'm going to use same value of resistors and capacitors in both sides. So it's easy to calculate Z1. We did it before, and Z2, right? So this has one pole. This has a root and a pole. Furthermore, I can take the sum. I need the sum. And so here's the sum of the two. I've just cross-multiplied, put them over a common denominator. And then I take the ratio of Z1 to this, and note that I have a 1 over 1 plus RCS in both cases that I get rid of. The CS here combines with the R, and I have the numerator of Z1 plus Z2 as my denominator. And then if I multiply out this, I get a 2 RCS term in the middle, which I add to this one. I get 3 RCS, and the rest go on. Now, the interesting case is when S equals S squared, no, sorry, S equals 1 over RC, in which case RCS is 1, except that it's really omega equals 1 over RC. And S is j omega, so when I square it, I get minus 1. So I can imagine the case where S is such that RCS squared is minus 1, in which case this term cancels that term, and the RCS here cancels that, and I have 1/3. So as long as I make this amplifier have a factor of 3, I'm satisfying my condition. By the way, how do you get an amplifier to get a factor of 3? Well, you start with a regular op-amp, and you'd have feedback where the voltage divider cuts down the output by a factor of 3 and feeds it back in. So this acts as an amplifier with a factor of 3. And so if we set up this amplifier, we should get out a sine wave frequency. Because we have an S, it only works at one S, that we have this condition, and that S will be determined by 1 over RC, the RCs that we have in either of these places.